Mechanical properties of fluids, chapter 10, physics. Let's continue from where we left yesterday. We had completed Bernoulli's principle. Now let's go to venturimeter. Topic, subtopic, venturimeter. The venturimeter is a device to measure the flow speed of incompressible fluid. The venturimeter is a device. It is used to measure the flow speed of an incompressible fluid. It consists of a tube with a broad diameter and a small constriction at the middle, as shown in figure 10.11. It consists of a tube with broad diameter, maybe this one here, a tube with broad diameter and a small constriction at the middle, as shown here. This whole thing, okay, this is not this wire. The broad diameter is this one, and a small constriction or a narrow constriction at the middle. And a mammometer in the U-tube shape is connected as shown here. A mammometer in the form of a U-tube is also attached to it with one arm at the broad neck and the other at the constriction as shown in figure 10.11. The mammometer contains a liquid of density rho m. The speed v1 of the fluid through the tube at broad neck area A1 is to be measured from equation of continuity. The speed v1 of the liquid flowing through the tube at the broad neck area, meaning the speed of the fluid it's flowing to this area is, let's take it as v1. It is measured from the equation of continuity. Equation of continuity is av, which is equals to constant. So from that we will get at the constriction it will become two different areas. So v2, which is equals to av1 by small a, which is the area of this small area or narrow area. Then using Bernoulli's equation, and here for h1 equals h2, I showed a special form of Bernoulli's equation yesterday, which was when there is a horizontal tube, there is no potential difference between the two ends. So basically it will be of same height, where h1 equals h2, delta u, which is equals to 0. So P1 plus change in kinetic energy per unit volume, or half rho V1 square, which is equals to P2 plus half rho V2 square, but instead of that they have substituted V2 as A by A V1 whole square, so that P1 minus P2, the difference between pressures in the narrow end and this end here, to be half rho V1 square A square by A, A by A whole square minus 1. This pressure difference causes the fluid in the U-tube connected to the neck to rise in comparison to the other arm. The difference in height edge measures the pressure difference. which is equals to P1 minus P2, which is equals to rho GH, or rho m, that is the density of the fluid, GH, the height difference between the two different fluids, which will get equal to this one. And we, from equating both of them, we will get that the speed at V1, which is equals to approximately this much. The principle behind this meter has many applications. The carburetor of automobile has a venturi channel nozzle through which air flows. Before that, let's derive this equation ourselves to get a clear understanding of how, what, and why it works. Chapter Mechanical Properties of Fluid. Let's see that subtopic venturi meter. What is the use of a venturi meter? It is used to measure the speed of fluid passing through the pipe. And it is specifically, the fluid is incompressible for it to follow Bernoulli's principle. It is based on Bernoulli's principle and equation of continuity, so it should be incompressible fluid, as both of them depend on incompressible fluid. Now, the venturi meter is, if this is the pipe, the venturi meter will have a short constriction like this. This is the venturi meter. These are the two pipes. If we consider the area of the pipe to be A and the constriction or narrow end to be small a, and consider the velocity of particles here v1 and here v2, here they again come back to e1, but leave that be for now. And we connect a mammometer, a U-tube mammometer here. A mammometer like this. And what is the use of the mammometer? It is used to measure the pressure difference. Basically, we know that the pressure at the broader end should be more than the pressure at the narrow end, because if not, we know that the velocity at broader end is smaller than the velocity at the narrow end. As the fluid goes from broader to here, this region, the velocity should increase, v2 should be greater than v1. But because of the concentration of the streamlines. But what will provide this acceleration for v1 to rapidly increase to v2 is the pressure difference. So that means, there, due to conservation of energy, there must be a pressure difference between this area and this area. And this, for this pressure difference, p1 should be greater than p2. If this is 2 and this is 1, For V2 to be greater than V1, P1 should be greater than P2. Because of that, if we see the levels of the liquid here, how a mammometer measures liquid is, if they are at the same level, then that means the pressure differences at the 2 points is same. If the liquid inside is at same level, like this in the same level, then that means the pressure difference between them is same. But if not, if they are not at the same level, let's assume we know that pressure 1 is at this pressure is much greater than pressure 2, so that means this level should be smaller than this level. This should push on this liquid more than this one, so there must be the level of liquid here must be greater than this one. And we can measure the pressure difference through rho gh formula, where we will get the excess pressure here. We know that rho, if we assume the density of the fluid, if this fluid uh, has a density of rho m, then the excess pressure P1 at one area minus P2 must be equal to rho m g and this height difference between the levels h. This is pressure difference formula. Now going to the venturi meter derivation, where we need to find this velocity here v1. We need to find v1 velocity in the tube. That we can find out. First we will relate through equation of continuity. Based on equation of continuity, av, which is equals to constant, so a1, no, let we took it as the area of the smaller narrow constriction. Let's take it as small a. If we took it as small a, then a v1, which is equals to small a times v2. Now we don't need v2, we don't need to find the speed of the liquid in this one. We only need to find out the speed of this one, this liquid, the total pipe. We want to find out the speed of liquid in the total pipe. That is the main use of it. There is no need to find the speed of liquid inside this what is it? Yeah, narrow constriction. So no need for this. So we will send this side. And next, in Bernoulli's equation, we will substitute this formula AV1 by A for V2. In place of V2, we will substitute A by A V1, through which we will not get our non-essential V2 and we will get our essential V1. Now we know Bernoulli's equation. Bernoulli's equation is P plus half rho V1 square or V square plus rho G H, which is equals to constant, which is equals to constant. So based on this, and if we take for these two surfaces 1 and 2, the height difference delta H, which is equals to 0 because they're at the same elevation, so potential energy will also be 0. This term will become 0, and considering both of these surfaces, P at 1 plus half rho V1 square, which is equals to P2 plus half rho V2 square. Now we have the formula for V2 here from equation of continuity. From that we can substitute V2 in place of V2. P1 plus half rho V1 square, which is equals to P2 plus half rho, and V2 value is A by A V1 whole square. Now let's shift these terms here. This will go this side and this will come this side. Or the one we took is P1 minus P2. Okay. P1 minus P2, which is equals to half rho V1 square AA whole square minus half rho V1 square, which is equals to P1 minus P2. We have our above formula. This one, substitute that, rho mgh, which is equals to, now the common terms are, this is common, this is common, take that out, half rho V1 square A by A whole square minus 1. Now this is the density of the fluid, this is the density of the mammometer fluid. It is different, so we cannot cancel them out. I think so. Now what we need is this term, that is the velocity of fluid inside the pipe. So let's shift everything towards left side and get, or right side. Based on it, we should isolate this V1. For us to isolate V1 square, which is equals to rho mgh times 2, or 2 by A whole square minus 1 and rho f. I think we shifted everything. 2 is here, rho f is here, A is here. Now V1 is left alone. Now finally V1, or V, the velocity of fluid inside the pipe, which is equals to root of 2 rho mgh by A whole square minus 1 rho f. That is rho of the fluid. This is rho of the mammometer. And this is the final derivation of the venturimeter, through which, what is the use of the venturimeter is, if in industrial scales, if two there is a pipe like this and it's a steady flow pipe and there is an incompressible fluid flowing through this pipe, and we want to measure the speed of the fluid inside, in such a case we use the venturimeter to find out the speed. That is the use of the venturimeter. This is the derivation they use to find the speed using the venturimeter. Okay, let's go back to NCERT. The principle behind this meter has many applications. The carburetor of automobile has a venturi channel nozzle through which air flows with a high speed, and the pressure is then lowered at the narrow neck, and petrol or gasoline is sucked up in the chamber to provide the correct mixture of air to fluid necessary for combustion. filter pumps or aspirators, Bunsen burner, atomizers, and sprayers used for perfumes or to spray insecticides work on the same principle. Basically, what they mean is basically if we take an example, let's go back to word here. If we take a venturi meter like this, it's not only used as for measuring speed of fluid, it can also be used for other things using Bernoulli's theorem or Bernoulli's principle. If this is a venturi meter, there is water flowing through like this or something like that. Air, let's assume there is air flowing through like this and coming out through like this, and also here as well. This is air. Now, now we know that this, let's assume this area which is A, and again this area which is equals to A. Obviously, from seeing this, A is much greater than this A, small a, and from equation of continuity we can say that A, if the air here is going with a speed v1 and this is v2, okay, using equation of continuity we can say that, or based on our intuition we can say that v2 is greater than v1, and using equation of continuity if you want to prove it, then av1 which is equals to av2, and since a by a which is equals to v2 by v1, because a is much greater than a, v2 is also much greater than v1, and this we can understand. But what leads to the increase in the speed? It's due to the pressure difference. Because of a higher pressure, because the pressure is compensating for increase in speed. So because of that, because here there is a high pressure and here there will be a low pressure at this point. At this point there will be a low pressure because there needs to be a force that needs to compensate for increase in velocity, and that will be pressure. Pressure will reduce here in this portion to compensate for the increase in speed. Because of that, if we take pressure differences, then here if we take the pressure to be P2, here we take it as P1, P2 is smaller than P1. And we can use this principle. Now let's draw the venturi meter again. Air is going like this, coming out like this, speed is more here, and this is a low pressure area. Now if we connect this to, let's assume, a perfume bottle like this. Now because of this low pressure area created here, low pressure area, because of, we know the principle above I told you. Now because of this low pressure area, the water or the perfume will come up like this. will come up and flow out like this, becoming a sprayer. And in case if it was petrol or gasoline, if it was petrol or something like that, it will provide a mixture of needed based on calculations. They will take a certain size venturimeter for the required need of mixture of air and fluid or petrol for necessary combustion. That will be provided using the venturimeter. They said about some carburetor or nozzle or something like that. But basically, using this low pressure area, we can suck up the fluids here, fluids inside, which will come up, and this will be acting as a sprayer. That is the use of application of venturimeter, and this is based on Bernoulli's theorem, Bernoulli's principle, which basically is stating that like the higher the speed, lower the pressure in case of like when it's moving from larger end to smaller end or narrower end. Okay, let's go back. Let's read that again. Principle behind this meter has many applications. The carburetor of automobile has a venturi channel nozzle through which air flows with a high speed. The pressure is then lowered at the narrow neck, and the petrol gasoline is sucked up in the chamber to provide the correct mixture of air to fluid or fuel necessary for combustion. Filter pumps or aspirators, Bunsen burner, atomizers, and sprayers used for perfumes or to spray insecticide work on the same principle. The spray gun piston forces air at high speeds, causing a lowering of pressure at the neck of the container. This is also another way of showing the venturing meter. Basically, this is larger area and this is smaller area. And when air comes out very fast here, because of the narrow area, it will become even more faster, and there is a pressure difference created here. And because of that, when we push it fast, it will spray. It will spray along with air, whatever the fluid is placed in this bottle. Now let's see something, an example. Blood velocity. The flow of blood in a large artery of an anesthetized dog is diverted through a venturi meter. The wider part of the meter has a cross section area equal to that of the artery, where area is 8 mm square. The narrower part has an area of 4 mm square. The pressure drop in the artery is 24 pascal. Now, what is the speed of blood in the artery? Basically, we wanted to find the speed of blood in the artery, so that we use the venturi meter. Now we connect the artery of a dog, an anesthetized dog, to a venturi meter. And basically, we also know the equation here, basically substituting it in the equation. And we can take the density of blood from the table, which is 1.06 into 10 power 3 kg per meter cube, slightly more than water. The ratio of area, which is A by A, which is 8 by 4, which is equals to 2. Now equation 10.17. We already know the pressure drop. Basically here, rho mgh from this equation here, rho mgh, this rho mgh is basically delta P or P1 minus P2. This is a pressure drop or excess pressure. Because of that, rho mgh directly they gave, we don't need to calculate it, they directly gave that the pressure drop is 24 pascal. So we substitute 24 in the place of rho mgh, we will get root of 2 times 24 by 1060 kg meter kg per meter cube into 2 square minus 1, which we will get it as approximately 0.123 meter per second. And let's see another section here, blood flow and heart attack. Bernoulli's principle helps in explaining blood flow in artery. The artery may get constricted due to the accumulation of plaque on its inner walls. In order to drive the blood through this constriction, a greater demand is placed on the activity of the heart. The speed of the flow of the blood in this region is raised, which lowers the pressure inside the artery, may collapse due to the external pressure. The heart exerts further pressure to open this artery and forces the blood through. As the blood rushes through the opening, the internal pressure once again drops due to same reason, leading to repeat collapse. This may result in a heart attack. Basically what that means is, let's go to word. Let's assume an artery. We all know what an artery is, I believe. Artery before plaque accumulation or fat accumulation. If we take an artery, it will be something like this. Blood will be flowing like this, or red blood cells will be flowing like this. Let's not indicate it as red blood cells. Let's just take it as blood. It's a fluid. It's going like this. Now, artery after plaque accumulation. Plaque is, let's assume, cholesterol or fat or something like that. It's not clearly mentioned. It's something that's getting accumulated in the artery. Let's assume something like this. Now, when the blood is flowing like this, the blood will get like this. Okay, basically, if we see here, this seems very similar to a venturimeter. A venturimeter where there is a broad end, there's a broad end here and a narrow end. There's a two broad ends, one narrow end, like this. In such a case, we can understand that the pressure in this area, I mean the velocity of blood in this area, let's take v2, v1 here. The normal broad end's velocity of blood is v1, and at this end it is v2. We know that v2 is greater than v1. Because of the accumulation of the streamline flows, the speed will increase, the pressure will decrease. Pressure will decrease. And because of this pressure decrease, due to the accumulation, pressure will decrease in this area. Because of that pressure decrease, an unbalance with the atmospheric pressure is created. And the atmospheric pressure will act on this artery, or outer external pressure will act on this artery at this point. Due to low pressure, then imbalance in forces is created, and there will be an external force acting on this artery, and because of this external force, Basically, the artery will collapse. Artery collapse. If this artery is collapsed, the heart, because the blood is not flowing, will try to pump blood even more faster to open up this collapsed artery. Heart will pump the blood faster so that the collapsed artery may open up. And if because of that heart pumping blood faster, the artery will be forcefully somewhat opened up. Let's assume it's something like this. But again, if there is accumulation here, there will be same situation again with blood flowing. There will be low pressure area. Again, the atmosphere will act, collapse this, and again the heart will need to pump blood more with more force so that this opens up. The repeat of this cycle will cause a heart attack. That is what they explained there. The artery collapsing and the heart pumping the blood again. Again, the artery collapsing, the heart pumping blood even more with more force. It will collapse again and again. The heart will also stop beating. Let's see it again. Bernoulli's principle helps in explaining blood flow in artery. The artery may get constricted due to accumulation of plaque on its inner walls. In order to drive the blood through this constriction, a greater demand is placed on the activity of the heart. The speed flow of the blood in this region is raised, which lowers the pressure inside the artery, and the artery may collapse due to the external pressure. The heart exerts further pressure to open up this artery and forces the blood through. As the blood rushes through the opening, the internal pressure once again drops due to same reason, leading to repeat collapse. This may result in heart attack. That's with the blood flow and heart attack. Now let's go to dynamic lift. Dynamic lift is the force that acts on a body such as an aeroplane wing, a hydrofolly, or a spinning ball. By virtue of its motion through a fluid, in many games such as cricket, tennis, baseball, or golf, we notice that a spinning ball deviates from its parabolic trajectory and it moves through the air. This deviation can be partly explained on the basis of Bernoulli's principle. Okay, what they are talking about is about dynamic lift. What is dynamic lift? This dynamic lift is a force that acts on a body. It's a force that acts on a body like an aeroplane wing, a hydrofolly, or a spinning ball. Why it acts is due to the virtue of motion of this particle or ball or wing through a fluid. Due to virtue of motion, it will act. As for how we experience this dynamic lift, because of this dynamic lift, the aeroplane will lift into the air. When we kick a soccer ball or a football, the ball, if the ball spins, it will twist from its original, or it will swirl in a way that is different from the parabolic trajectory, and this can all be explained by dynamic lift. And one more name is Magnus effect, and these are all based on Bernoulli's principle. Now if we consider ball moving without spin, a fluid streaming past a static sphere, basically this is a ball, and it's just there, it is fixed in that position, and there is air, water, or whatever it is that is moving past this ball. shows the streamline ball moving without spin. It's not stationary, it is moving. It is moving, but it's not spinning. It's moving. Ball moving without any spin shows the streamlines around a non-spinning ball moving with a relative to a fluid. From the symmetry of streamline, it is clear that the velocity of fluid or air above and below the ball at corresponding points is the same, resulting in zero pressure difference. The air therefore exerts no upward or downward force on the ball. Before explaining that, let's see the ball moving with spin also. Streamlines for a fluid around a sphere spinning clockwise. Now ball moving with spin, a ball which is spinning drags air along with it. If the surface is rough and more air will be dragged. This figure shows the streamlines of air for a ball which is moving and spinning at the same time. The ball is moving forward and relative to it, the air is moving backwards. Therefore, the velocity of air above the ball relative to the ball is larger and below it is smaller. The streamlines thus get crowded above and rarefied below. This difference in velocities of air results in pressure difference between the lower and the upper faces, and there is a net upward force on the ball. This dynamic lift due to a spinning ball is called as the Magnus effect. Now let's see third section as well. Aerofoily or lift on an aeroplane or an aircraft wing. This 10.13 figure shows an aeroplane wing, air flowing past an aerofoily. If we see here as well, the concentration of streamlines is much more in the above the plane wing, and much less below the plane wing. This shows an aerofoil, which is a solid piece shaped to provide an upward dynamic lift when it moves horizontally through the air. The cross section of the wings of an aeroplane looks somewhat like that of an aerofoil shown in figure 10.13c with streamlines around it. When the aerofoil moves against the wind, the orientation of the wing relative to the flow causes the streamlines to crowd together above the wing more than below it. The flow the flow speed on top is higher than that below it. There is an upward force resulting in dynamic lift of the wings, and this balances the weight of the plane. The following example illustrates this. Okay, let's go toward the three cases. First case, ball moving in fluid without spinning. If we see a ball that is moving without spin, velocity in this direction, then if we see the streamlines, it will be something like this. If there are three streamlines here, there will be uniform number of streamlines here as well. The velocity will also be similar in both cases. The velocity will also be similar in both cases. Velocity will also be same. Because of that, there is no net pressure difference. The pressure here, if it is P1 and this is P2, both pressures will be equal. Because of that, there will be no difference there. The ball, if without spin, if it's moving in air, it will follow the parabolic trajectory. It will go first. If it is thrown upward, it will go like this and fall down like this, parabolic trajectory. But things change when we come to a ball moving with a spin. ball moving with spin. Now let's assume there is a ball like this and it is spinning like this in a clockwise direction. Now let's assume there are airways going like this and like this, streamlines going like this. And if we see clearly in this direction, in the lower hemisphere of the ball, if we see this part of the ball, if we see that the ball will be moving in direction of this streamline, thus enhancing the streamline. More airways will be concentrated here. Basically, because the ball is spinning in this direction, it is in the direction of the streamline, in the downward position. It is following with the streamline or amplifying the streamline. Because of that, there is an increased concentration of streamlines here. There is no crossing, it's just shown like this. But if we see in the top hemisphere of the ball, this one, the direction is opposite to the direction of the streamline. Because of that, there is obstruction of the streamlines. They will get accumulated here. They'll get accumulated here, and because of this obstruction here, there will be more concentration of streamlines, which causes decrease in velocity. This velocity, because it's obstructing the wind flow, this velocity, if we take v1 and v2 will be more than v1. And because of this reason, we know that the high speed, high velocity will create a pressure difference, that is low pressure. It will create a low pressure environment. Because of this pressure, which is P2 if we take, and this one P1 if we take, P2 will be less than P1. Because of that, this external pressure will push it this side because of an imbalance in pressure, and the ball, instead of going like this, it will go something like this because of this pressure difference. This is called as Magnus effect. Now third case is aeroplane wing. Now if we see an aeroplane wing, it will be something like this, and it will be in such a way that when it is cutting through the air, it will be arranged in such a way that the velocity here, if we see when it's flying, there might be a stopper or the movable things will come down like this to obstruct the airflow here, thus creating lower velocity and accumulation of streamlines here. And here it will be dynamically, the air, there is no obstruction in this direction, so there is clearly more streamlines going here. And here if we see, there is less velocity. Basically, we should observe the velocity. Because there is an obstruction, the streamline should have less velocity. Here velocity, if we take v1 and v2, v1 must be greater than v2. Because of this, there is no obstruction here. Because of the position, because there is no obstruction, v1 should be, this velocity should be greater than this velocity. And because of less velocity, I mean high velocity, pressure must be less. There will be creation of a less pressure environment, less pressure surrounding. Because of this less pressure, there will be an upward force due to atmospheric pressure, there's an imbalance created below and above the wing. Because of that, there will be air pressure acting upwards that will push the flight upward. That is why an aeroplane flies. Let's go back. Now that's that. We can indeed read it again. Dynamic lift is the force that acts on a body, such as aeroplane wing, hydrofoil, or a spinning ball by virtue of its motion through the fluid. In many games, such as cricket, tennis, baseball, or golf, we notice that a spinning ball deviates from its parabolic trajectory as it moves through the air. This deviation can be partly explained on the basis of Bernoulli's principle. Ball moving without spin shows the streamlines around a non-spinning ball relative to fluid. From the symmetry of streamline, it is clear that the velocity of fluid air above and below the ball at corresponding points is same, and the resulting in zero pressure difference. The air therefore exerts no upward or downward force on the ball. Ball moving with spin, a ball which is spinning drags air along with it. If the surface is rough, more air will be dragged along. Show the streamlines of air moving forward, and related to it, the air is moving backwards. Therefore, the velocity of air above the ball relative to the ball is larger, and below it is smaller. Velocity of air above the ball relative to the ball is larger, and below it is smaller. The streamline thus gets crowded and rarefied below. The difference in velocities of air results in pressure difference between the lower and upper surfaces, and there is a net upward force on the ball. And this dynamic lift due to spinning is called as Magnus effect. Okay, then let's go to aerolift or lift on aerofoil or lift on the aircraft wing. Shows an aerofoil which is solid piece shaped to move forward, an upward dynamic lift which it moves horizontally through the air. The cross section of the wings of an aeroplane looks somewhat like that of an aerofoil shown in the 10.13c. When the streamlines around it, when the aerofoil moves against the wind, the orientation of the wing relative to flow direction causes the streamlines to crowd together above the wing more than those below it. The flow speed on top is higher than at below it. There is an upward force resulting in dynamic lift of the wings. This balances the weight of the plane. The following example illustrates this. Let's see the example. A fully loaded Boeing aircraft has a mass of 3.3 to 10 power 5 kg, 330 tons approx. Its total wing area is 500 meters square. It is an it is in level flight with a speed of 960 kilometers per hour. Now our question is, estimate the pressure difference between the lower and the upper surfaces of the wing. Estimate the fractional increase in the speed of the air on upper surface of the wing relative to the lower surface, and the density of air is rho is equals to 1.2 kg per meter cube. Second question they asked is estimate the fractional increase in speed of the air on the upper surface. Okay, difference between speed they are asking. They're asking the difference between speed. Okay, why they gave weight of the Boeing aircraft is not weight, mass of the Boeing aircraft is because we can calculate the weight of the Boeing aircraft, that is mg of the Boeing aircraft, through which we can identify the force that is acting upward and it is supporting the weight of the Boeing aircraft. We can equate it to the pressure or the upward thrust or force. Delta P dot A, which is equals to force or weight, which is equals to 3.3 into 10 power 5 into 9.8. And we can calculate the pressure difference from this formula. Using that, we will get approx 6.5 into 10 power 3 Newton per meter square. If we ignore the small height difference between the top and the bottom sides, the pressure difference between them is delta P, which is equals to okay, what we ignored here is we are basically using Bernoulli's principle here, where delta P, which is equals to delta kinetic energy per unit volume and kinetic energy, I mean potential energy per unit volume. Because we neglect the small height difference, we can take it directly as we can ignore potential energy difference, through which we will get this equation. And v2 is the speed of air above the upper surface and v1 is the speed under the bottom surface, which we will get it as 2 delta p by rho v2 plus v1, and v2 plus v1, which is the total speed of the aircraft, and v2 plus v1 by 2, which will get the total speed of the aircraft, and multiplying it with 2, we will get v2 plus v1, and substituting it here, v2 minus v1 by v average, which is equals to delta p by pv average square, which is approximately equal to 0.08. The speed above the wing needs to be only 8% higher than below it to lift an aircraft of 3.3 into 10 power 5 kg. Now let's come to the next main topic, or before that let's take a 10-minute break. Okay, then let's continue. Viscosity, our main topic. One of the main topics, viscosity. Most of the fluids are not ideal ones and offer some resistance to motion. That's true. Most of the fluids are not ideal fluids and offer some resistance to the motion of fluid. This resistance to fluid motion is like an internal friction analogs to friction when a solid moves on a surface. And instead of friction, we call it as viscosity. This force exists when there is a relative motion between layers of liquids. Okay, we saw that streamlines, although they seem like having same velocity, that is not true. Different streamlines may have different velocity. As long as the streamlines do not intersect each other, that is called as a steady flow. So even if it is a steady flow, different streamlines may have different velocity, and due to different layers of water moving in different velocity with relative motion between them, basically relative velocity between them, one layer is moving faster than the lower one. Because of that, there will be some resistance to this motion, that is called as viscosity or viscous force. This force exists when there is relative motion between layers of liquids. If we consider a fluid like oil enclosed between two glass plates in figure 10.14, this figure, a layer of liquid sandwiched between two parallel glass plates in which the lower plate is fixed and the upper plate is moving on the right with velocity v. Okay, this is the figure. This is the figure, this whole thing. These are two glass slides. This is a droplet of oil magnified to a large extent. This is the gap between the two plates. This is oil. Now, this lower plate is fixed. It's not going to move. But this upper face or slide is not fixed, and there is a force applied on this slide. Because of that, this slide will move forward. And because of the sticking of the oil to this surface, the oil will also move like this, where this is moving with this much velocity, there's reduce in velocity, reduce in velocity, reduce till it is minimum at the bottom where it's not moving at all. There is a relative motion between the different layers of the oil droplet. Now this is similar to shear stress diagram, but let's not consider it here. Delta x is equals to v delta t. We consider a fluid like oil enclosed between two glass plates. The bottom plate is fixed while the plate will move with a constant velocity v relative to the fixed plate. If oil is replaced by honey, a greater force is required to move the plate with the same velocity. Hence, we say that honey is more viscous than oil. The fluid in contact with the surface has same velocity as the other surfaces. Okay, for this plate to move like this, there must be resistance here, because for sliding this layer there must be resistance here, 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 and here. So if we take oil here, we need to apply a certain amount of force to make it appear something like this. And if we take honey, it will be even more than oil. Because of that, we say that oil is less viscous than honey, or honey is more viscous than oil, because it needs more force to uh, show that sliding between surfaces. Hence, the layer of liquid in contact with the fluid in contact with the surface has the same velocity as the surface. Hence, the layer of liquid contact with the top surface moves with a velocity v, and the layer of liquid in contact with the fixed surface is stationary. Okay, the upper surface, which is like in contact with the topmost moving slide, will move with same velocity as the slide, and the downmost surface, which is like connected to the slide, which is fixed to the slide, will not move and it will be fixed there. The velocities of layers increase uniformly from bottom 0 velocity to top velocity v. They will increase uniformly. For any layer of liquid, its upper layer pulls it forward while the lower layer pulls it backward. This results in a force between the two layers. This type of flow is known as laminar, where they are parallel. The layers of liquid slide over one another as the pages of a book do when it's placed in a flat table, and as a horizontal force is applied on the top of the cover. When a fluid is flowing in a pipe or a tube, then the velocity a fluid is flowing in a pipe or a tube, then the velocity of the liquid layer along the axis of the tube is maximum and decreases gradually as we move towards the wall when it becomes zero. Okay, when a fluid is flowing through a pipe or a tube, then velocity of liquid layer along the axis of the tube is maximum and decreases gradually as we move towards the wall when it becomes zero. The velocity on cylinder surface in a tube is constant. Basically, if we take a pipe here, water is flowing through, then the water in the axis that is in the center of this pipe will have maximum velocity, and as we go from center to towards the wall, the velocity will continuously decrease, and the velocity of particles at the wall, which is approximately equal to zero, and it will remain constant. On account of this motion, a portion of liquid which at some instant has a shape ABCD takes the shape of AEFD after a short interval of time. Okay, wait a second. This is velocity situation of for viscous flow in a pipe. Minimum at the walls, maximum at the center. On account of this motion, a portion of liquid which at instant has a shape ABCD, where it is. Yes, this one. At here it is ABCD shape, and after some instance it will become ACFD shape. After a short interval of time, delta t, during the time interval, the liquid has undergone a shear strain of delta x delta L by delta L. This is equal to tan theta. Since the strain is flowing, fluid increases with time continuously. Unlike a solid, here the stress is found experimentally to depend on rate of change of strain. Let's understand what they're saying here. They're talking about shear strain, which is equal to delta x by L. Since the strain is in a flowing fluid increases with time continuously, strain is increasing continuously. That is true. Unlike a solid, here the stress is found experimentally to depend on rate of change of strain or strain rate, that is delta x by L delta t or V by L, instead of strain itself. We saw that strain was directly proportional to stress according to Hooke's law, but here it is experimentally found out that the stress is not directly proportional to strain, but instead it is directly proportional to rate of change of strain or strain rate, that is delta x by L delta t, instead of strain itself. The coefficient of viscosity, pronounced as eta, for a fluid is defined as a ratio of shearing stress to the strain rate. The coefficient of viscosity for a fluid is defined as ratio of shearing stress to strain rate. The SI, this is the formula. I'll see if I can write it again. The SI unit of viscosity is Poiseuille or PL. Its other units are Newton second per meter square or Pascal second. The dimensions of viscosity are ml power minus n t power minus 1. Generally, thin liquids like water, alcohol, etc. are less viscous than thick liquids like coal tar, blood, glycerine, etc. The coefficients of viscosity for some fluids are listed in table 10.2. We point out facts about blood and water that you may find interesting. As table 10.2 indicates, blood is thicker, more viscous than water. Further, at relative velocity, the blood remains constant between 0 degree and 37 degree. The viscosity of liquids decreases with temperature while it increases in case of gases. Let's see that, read that again. Basically, let's go to Word. Okay. If we assume there is three layers of water like this, and this is the cover slip which is moving, and this is one more slide that is below. Now we apply a force for or this slide, so it will move along with this slide. Now because it is moving, it will pull this water due to relative motion. This layer which is moving will pull the water this layer forward, or basically instead of saying it will pull it forward, because there is a viscous force, basically this second layer will apply a force in this direction on this layer that is moving with the cover slip. It will apply a force in that direction, and because of Newton's third law, this water will also apply an equal and opposite force on this fluid in this direction. Same way, this structure will become into this structure because of Newton's third law. Now they defined viscosity, and based on this, this is similar to shear strain. This is delta x which we can consider it to be equal to v delta t. Now if we take it as shear strain, normally according to Hooke's law, strain or stress, which is directly proportional to strain, but in this case it is found that this is not applicable, and instead stress is directly proportional to not strain but strain rate. And based on this stress, which we can write as force by area, which is equal to proportional constant eta, which is viscosity, eta viscosity times strain rate, which is equals to delta x by L delta t. Now this will go that side, FL delta t by A delta x, which is equals to eta. This is the formula for eta. Or we can write this in another way. we know that delta x by delta t is equals to delta v, not delta v, just v, velocity basically velocity, and delta t by delta x, which is equals to 1 by velocity. Now we know this, we can make it as fl by a times velocity, which is equals to, that came out different, but is equals to eta, or viscosity. This is the formula for viscosity. Depending on a similar Hooke's law where stress is directly proportional to strain rate, which is experimentally found out. And the SI unit is Poiseuille, a weird name to pronounce, but that's the SI unit. And we know that water, alcohol are less viscous than thick fluids like coal tar or blood or glycerine, etc. Now let's come back to textbook. That's basically a derivation for viscosity. Wait, this is not viscosity. This is coefficient of viscosity. The coefficient of viscosity. This is not viscosity. Eta is coefficient of viscosity. It's pronounced as eta, and it is coefficient of viscosity for a fluid, ratio of shearing stress to strain rate. Now measurement of coefficient of viscosity of a liquid, they gave something here. Maybe there's an explanation later, we'll see that later. Let's see the example. A metal block of an area 0.1 meter square is connected to a 0.010 kg mass via string that passes over an ideal pulley. This diagram itself, same. This is the example or diagram for this question. A metal block of area 0.10 meter square is connected to a 0.010 kg mass via a string that passes over an ideal pulley considered massless and frictionless, as in figure 10.15. A liquid with film thickness of 0.3 mm is placed between the block and the table. When released, the block moves to the right with a constant speed of 0.085 meter per second. Find the coefficient of viscosity of the liquid. Okay. They gave that this is a block and there is a liquid between the block and the table. And they gave how much speed it will move when it is released. And the masses of them they gave. The metal blocks moves to the right because the tension in the string, the tension is equal to the magnitude of the weight of the suspended mass. Thus, the shear force is F, which is same as tension, which is equals to mass into G, which is approximately equal to 9.8 into 10 power minus 2 Newton. Now shear stress on the fluid, which is equals to force by area, that is area of the bottom surface of the block. Mass of the block is not given, but area of the block is given, which is 0.10 mm square, no, meter square. Now strain rate, which is equals to V delta T by L delta T. Delta T get cancelled. We will get V by L. Velocity they gave already, which is 0.085, is equals to by length. Also they gave, yeah, length they gave it as, that is the basically the height or thickness of the fluid, that they give it as 0.30 mm, which we can convert as 0.3 into 10 power minus 3 meter. Now eta, which is equals to stress by strain rate, substituting all these values, we will get it as 3.46 into 10 power minus 3 pascal second or poisson. Now viscosities of some fluids. I have a one doubt. What is difference between viscosity and coefficient of viscosity? Let's find out. Property of fluid that resists the relative motion between its layers. In simple terms, it tells us how thick or sticky a fluid is. Measure of viscosity, numerical constant, and used in equation. It appears in law of viscosity. This equation, which we still didn't get, but we will get, force, which is viscous force, which is equal to eta times A by dV by dx. dV by dx is the shear strain. Viscous force we will get from this formula. Okay, let's go back. Viscosity in terms of millipoisson is basically viscosity here is viscous coefficient itself. This viscous coefficient is actually coefficient of viscosity is basically a constant, a proportionality constant, which we got from stress, which is directly proportional to strain rate. The constant of proportionality there is coefficient of viscosity. Now the coefficient of viscosity of water, which is in 1 into 10 power minus 3, it decreases with temperature, they said. There is some extra information about that here listed. We point out facts about blood water. The viscosity of liquid decreases with temperature. As temperature decreases, the viscosity of liquids will decrease, while it increases in the case of gases. In liquids, liquids already have strong intermolecular forces. Viscosity on liquids mainly depends on how tightly molecules are bonded together. When temperature increases, molecule gain kinetic energy. They can more easily overcome intermolecular attraction. Viscosity decreases with temperature in liquids. Okay, it's inverse proportionality. As temperature increases, viscosity decreases. As temperature decreases, viscosity increases. Because of kinetic overcoming their intermolecular forces, they can go easily. In gases, intermolecular forces are negligible. Viscosity in gases mainly due to momentum transfer between molecules when they collide. At higher temperature, molecules move faster. Collisions are more frequent, more effective in transferring momentum between layers. This makes resistant to flow increase. Viscosity increases with temperature. Okay, now we saw the answer for that. Now water at 20 degrees viscosity is high, at 100 degrees viscosity is low. Blood 37 degrees it is at 2.7. Machine oil at 16 degrees it is highly viscous. At 38 degrees it is less viscous, very less viscous. Glycerine at 20 degrees it's 830 viscous, 830 into 10 power minus 3 poisili. Honey also 200, which is very high. Air, which is around 0.017 at 0 degrees, it increases slightly at 40 degrees due to collisions. Let's go to now one of the next topics. It's a subtopic under viscosity, I believe. Yeah, it's under viscosity, 10.5 viscosity. Stokes law, first subtopic under viscosity, and also the last, I think. Stokes law. When a body falls through a fluid, it drags a layer of fluid in contact with it. A relative motion between the different layers of fluid is set. As a result, the body experiences a retarding force. Falling of a raindrop and swinging of a pendulum bob are some examples of such motion. It is seen that the viscous force is proportional to the velocity of the object and is opposite to the direction of motion. The other quantities on which the force F depends on are viscosity eta for the fluid and radius A of the sphere. Sir George D. Stokes, 1819 to 1903, an English scientist, enunciated clearly the viscous drag force F, which is equals to 6 pi eta AV. This is known as Stokes' law. We shall not derive Stokes' law. Okay, before that, let's see what they're telling. No, let's understand what they're telling. When a body falls through a fluid, it drags layers of fluid in contact with it. Let's go to word. Here, when let's assume this is a ball, it's going with velocity this way. There will be air here. It will be going like this. Now, maybe due to friction between this and this streamlines, the ball will drag some airways or particles in this direction. And actually, we can understand it using Newton's third law. Basically, because it is moving, the ball is going to apply, no, the air is going to apply some force on this ball because it's going against the air streamlines. Because of that, the air is going to apply some force on the ball in this direction. And because of that, the ball will also apply some force on the air in the opposite, equal and opposite direction. Because of that, the air will be getting dragged along with the ball. That is what happens when our object falls through a fluid. Let's assume this ball has a radius of a. Now let's go back. When a body falls through a fluid, it drags a layer of fluid in contact with it. A relative motion between different layer of fluids is set, and as a result, the body experiences a retarding force. Actually, it's not only that force. If we come back toward here, and because of this particle, some air particles are having a force are having a force in this direction. They will move in this direction, and some airways will again be going in this direction, and these airways will have viscous force, and again these fluids will also have. It's more correct to say this in liquids because they have high viscosity compared to air. It's moving through fluid, let's assume. This airway, it's going in this direction because it's getting dragged along by the ball. There's another airway or streamline going in this direction. There will be viscous force due to intermolecular attractions, and this airway going this way will pull this airway, or I mean fluid, in this direction, and because this is connected to the ball, this, because of Newton's law, this airway or this streamline will also apply equal and opposite force on this streamline, and this will again be transmitted to the ball, where the ball will experience a net retarding force due to many streamlines. Due to many streamlines, it will experience a net retarding force. A relative motion between the different layers of the fluid is set, and as a result, the body experiences a retarding force. The falling of a raindrop and swinging of a pendulum bob are common examples of such motion. It is seen that the viscous force is proportional to the velocity of the object. Higher the velocity, higher the viscosity, and is opposite to the direction of motion, like friction. The other quantities which the force F depends on are coefficient of viscosity, determines the viscosity like nature of the fluid, and radius alpha of the sphere. I mean, not alpha, or we can take it as a of the sphere. And George G. Stokes, from 1819 to 1903, he's an English scientist, and he clearly he enunciated the viscous drag force F, and this viscous drag or viscous force, which is equals to F, which is equals to 6 pi eta AV. Friction, we know it as mu s times normal, or mu k times normal, or mu r times normal force. Here it is similar, same kind of force. It is opposing force, where viscous force, which is equal to 6 pi eta AV. This is the Stokes law, where force is directly proportional to eta. The drag is directly proportional to eta. It is directly proportional to the size of the object or radius of the object. It is directly proportional to the velocity of the object. The higher the velocity, the higher the force applied, because the higher the force the ball applies on the airways, the higher the force the airways also, or the fluid ways, will also apply on the ball. Because of that, it is directly proportional to velocity. Now this law is an interesting example of retarding force, which is proportional to velocity. We can study its consequences on object falling through a viscous medium. We can consider a raindrop in air. It accelerates initially due to gravity. As the velocity increases, the retarding force also increases. Finally, when viscous force plus buoyant force becomes equal to the force due to gravity, finally when the viscous force plus buoyant force becomes equal to the force due to gravity, the net force becomes zero, and so does the gravitation, I mean acceleration. The sphere raindrop then descends with constant velocity. Thus, in equilibrium, this terminal velocity VL is given 6 pi NAV is equals to 4 by 3 A cube rho minus sigma G. where rho and sigma are the mass densities of the sphere and the fluid respectively. We obtain v terminal velocity is equals to this much. So the terminal velocity Vt depends on the square and the radius of the sphere and inversely to the proportional viscosity of the medium. You may like to refer back to example 6.2 for their constant context. Okay, basically what they are saying here is, let's assume a raindrop is falling from the atmosphere when it just got condensed. The only force at that time is gravity. Gravity is acting downwards. And because of this gravity acting downwards, the raindrop will accelerate downwards. But as we go down, we know that pressure increases with depth. Because of that, the pressure as we go down will increase. And due to this increase in pressure, the buoyant force also will increase. And this will be opposite to the gravity. Along with the buoyant force, there will also be viscous force acting on this raindrop. And it will also be in the side of the buoyant force opposing the gravity. So we can say that at some point when the raindrop descends to some height above the surface, the buoyant force plus the viscosity will become equal to the mass of the object or the weight of the object or weight of the raindrop. Weight of the raindrop will become equal to the viscous force plus buoyant force. Or here I believe, and at that time the acceleration will become zero, and acceleration will become zero, and the particle will move with a velocity, a constant velocity known as terminal velocity. It is given by 6 pi n a v terminal, which is a drag, viscous drag. I believe they did not use buoyant force here. Buoyant force is equals to the weight of the water it has displaced. And for a raindrop or small objects, for relatively small objects, that can indeed be negligible. And so does the acceleration. The sphere raindrop then descends with constant velocity, thus in equilibrium, this terminal velocity, the force will be equal. So we equate the forces, that is the viscous drag, which is equals to weight of the object. Instead of weight of the object, we take mass into g of the raindrop. If we take it as a spherical object, then mass we can write as rho times v, which we can write as 4 pi by 3 r cube, which we can write as a cube if a is the radius of the object. Or they have considered buoyant force here. I'll do the derivation in word. Seems I have not shifted from word. Okay. Okay, I'll show what derivation I'm talking about. I'm talking about this derivation. This is the formula of force. This is viscous force. And at some point, this will be equal to the viscous force plus buoyant force, which will be equal to weight of the spherical object. Because of that, the acceleration will become 0 and it will attain a terminal velocity, due to which there will be no acceleration. Let's go back to Word. Now force, viscous force is equal to 6 pi eta a velocity terminal. It seems like mu, but it is velocity. This is viscous force. And coming to buoyant force, which is equals to weight of fluid displaced. Weight of fluid displaced is, let's take rho is the density of fluid. Volume of fluid, let's take it as spherical object, right? 4 by 3 pi a cube. This is the volume of the fluid. Rho times volume times g. This is the buoyant force. Now let's come to gravity force, which is equals to rho, that is, this is the mass of the fluid, medium, or should I write m rho f, which is equals to fluid medium density of fluid medium, rho object, which is equals to density of object. Force, which is force, gravitational force, which is equal to, we don't know the mass of the object, we will take density times volume, which is equals to mass. So volume of the object we can write as, since it's a spherical object, we can write volume as 4 by 3 pi a cube times g. It is similar to buoyant force, but it's gravitational force. Now we know that gravitational force, buoyant force, and viscous drag, where F viscous drag plus F buoyant force, which is equals to Fg at a certain point. Viscous force 6 pi net eta A times V terminal plus rho fluid 4 by 3 pi A cube times G, which is equals to rho object 4 by 3 pi A cube G. Now send the buoyant force this side, where we'll get 6 pi eta AV, which is V terminal, which is equals to, now 4 by 3 pi A cube and G common, take that out, 4 by 3 pi A cube G times rho of object, or density of object, minus density of fluid, and sending everything except V terminal to that side, we will get V terminal, which is equals to 4 by 3 pi A cube G by 6 pi eta A, where this A is radius of the object. Yeah, now this will become square, this got cancelled, pi pi cancel. Now 6, 2 3s are, 2 2s are, V terminal, which is equals to 2 by 9 eta A square G rho object minus rho fluid. This is the final derivation for V terminal velocity. This is the final derivation for terminal velocity. What Stokes law is? Stokes law just gives viscous drag, where viscous drag F, which is equal to 6 pi eta AV, where A is the radius, V is the velocity. It's not necessarily terminal velocity. For our relation, it will become terminal velocity. We take it as Vt. Here, it's not necessarily terminal velocity. 6 pi eta AV is equals to force. This is viscous drag or retarding force. Retarding force of a spherical object through a fluid medium. This force is directly proportional to velocity. Higher the velocity, higher the viscous force. This is based on Newton's third law. Higher the force applied by the ball on the streamlines, higher the force applied by the streamlines on the ball or the sphere. This A is, it's also directly proportional to the size of the object. The higher the size of the object, the higher the airlines it can or streamlines it can affect. It depends on eta, which is coefficient of viscosity, obviously, because it depends on fluid. If it is air, there is much less viscous force when compared to a ball going through water or honey. Okay, let's go back. Example 10.10, the terminal velocity of a copper ball of radius 2 mm falling through a tank of oil at 20 degrees Celsius is 6.5 centimeter per second. Compute the viscosity of the oil at 20 degrees Celsius. Density of oil is 1.5 to 10 power 3 kg per meter cube. Density of copper is 8.9 to 10 power 3 kg meter cube. Everything is given. All we need to find out is the eta value, which substituting in our below equation, no, above equation here, this one, we will get the value. Well, just eta which is equals to 2a square, difference between viscosity times g by 9 times of v terminal velocity, which will get to be approximately 9.9 into 10 power minus 1 kg per meter. Which, if we check here, oil, the viscosity of oil is not given here. Or if we take machine oil as well, this is into 10 power minus 3. So if we approximately take this as 10 into 10 power minus 1, which is equals to 1. So this is basically 100 into 10 power 2 into 10 power minus 3. No, it's not going to be enough. Okay, leave that then. Let's go to surface tension. The next main topic, that is surface tension. But before that, let's take a 5-minute break. Okay, that was much more than a 5 minute break, 5 minute break, but that's okay. Let's start with surface tension. Surface tension, you must have noticed that oil and water do not mix. Water wets you and me, but not ducks. Mercury does not wet glass, but water sticks to it. Oil rises up a cotton wick in spite of gravity. Sap and water rise up to the top of the leaves of the air. The hair of a paintbrush do not cling together when dry and even when dipped in water, but from a fine tip when taken out of it. Okay, let's see what they're saying here. We must have noticed that oil and water does not mix. This does not wet ducks. The mercury does not stick to glass, but water sticks to it. Oil rises up a cotton wick, that is against gravity. Sap and water rise up to the top of leaves of the tree. Hair of a paintbrush does not cling together when dry and even when dipped in water, but when dipped in paint and taken out, it will form a fine tip when taken out. All these and many more such experiences are related with the free surfaces of liquids. As liquids have no definite shape but have a definite volume, they acquire a free surface when poured in a container. Yes, like if we pour water in a container, they have the top surface which is free. It does not have definite shape but has a definite volume. They acquire a free surface when poured in a container. These surfaces possess some additional energy. This phenomenon is known as surface tension and it is concerned with only liquids as gases do not have free surfaces. Let us now understand this phenomenon. First subtopic is surface energy. A liquid stays together because of attraction between molecules. If we consider a molecule well inside a liquid, the intermolecular distances are such that it attracted to surroundings molecule. This attraction leads results in a negative potential energy for the molecule, which depends on the number and distribution of molecules around the chosen one. But the average potential of all molecules is the same. This is supported by the fact that to take a collection of such molecules, the liquid turns to this fact. What is the energy required for a molecule having a molecule at the surface? As mentioned above, roughly it is half the energy required to remove it entirely from the liquid, half the heat of evaporation. Finally, what is a surface? Since a liquid consists molecules moving about, there cannot be a perfect sharp surface. The density of the liquid molecules drop rapidly to zero around z, which is equal to 0, as we move along the direction indicated in figure. This way, in a distance of order of a few molecular sizes, and to disperse them far away from each other in order to evaporate or vaporize. The heat of evaporation required is quite large. For water, it is to the order of 40 kilojoule per mole. Let us consider a molecule near the surface. From this figure, only lower half side of it is surrounded by liquid molecules. There is some negative potential energy due to this, but Obviously, it is less than that of a molecule in bulk. The one fully inside, approximately it is half the latter. Thus, molecules on a liquid surface have some extra energy in comparison to the molecules in the interior. A liquid thus tends to have least surface area when external conditions permit. Increasing surface area requires energy. Most of surface phenomena can be understood in terms of, okay, we should have read that from here. In terms of this fact, what is energy required for having a molecule at the surface? As mentioned above, is roughly half the energy required to remove it entirely from the liquid, half the heat of evaporation. What is a surface? Since a liquid consists of molecules moving out, there cannot be a perfectly sharp surface. The density of liquid molecules drops rapidly to zero around z equals 0 as we move along the direction indicated in 10.16. Okay, whatever they said, it is kind of hard to understand, but let's see the diagrams and I will try to explain. Schematic picture of molecules in a liquid at surface and balance of forces. A molecule inside liquid, forces on a molecule due to other molecules are shown. Direction of arrows indicate the attraction repulsion. Same for a molecule at the surface, balance of attractive and repulsive forces. Okay, first what they are saying here is, let's take this is a container. Inside some point of this container, let's take there is a water molecule here. These are all surrounding water molecules, and there will be intermolecular attraction, repulsion, and other van der Waals forces that are acting on this water molecule due to all other water molecules. And due to this water molecule will have a potential energy of, let's assume, -1. This is the potential energy, and the average attractions portion repulsions will mostly get cancelled out, because if there is attraction in this way, there will also be an attraction this way, or repulsion in this way and repulsion in this way. Because of that, the net forces mostly get cancelled out and average will be 0. But because of these forces, there will be some potential energy in this water molecule because it's inside, and it will be around, it will be negative, let's around it's 1 whole or -1. Now let's consider this is the surface of a container or surface of a liquid. At this surface here, if this is water molecule at the surface, there are no water molecules here, not there, not possible on surface. In such a case, the only attraction repulsion will be from the latter, like the below half of the water molecule, that is from the water. So there will be a net force acting downward on these water molecules at the surface, and the potential energy they have will also be slightly more than the water molecule inside. It is more because we have a negative sign, -0.5. The surface water molecules have slightly higher energy than water molecules inside the water. This is what we call surface energy. They have higher surface energy, higher energy compared to inner molecules. Due to this extra energy and due to net force acting downwards, because there is no attraction or repulsion, or from here there is no force there, because of that there will be net force acting downwards. Because of that, whenever the water or liquid has possibility, allows, the circumstances allow it, the liquid will try to occupy as little surface area as possible. Due to the net attraction force, it will try to shrink as much as possible. Now let's read it again. A liquid stays together because of attraction between molecules. If we consider a molecule inside a liquid, the intermolecular distances are such that it is attracted to all surrounding molecules. That is what I said. This attraction, because of this attraction, it leads to a potential energy. This potential energy will be negative. This potential energy, we can say that potential energy can get cancelled out because all directions there will be potential energy, but that is not possible because potential energy is not scale, it is not vector, but it's a scalar quantity. All the individual potential energy due to individual molecules will get added up, and this will result in a negative potential energy for that single molecule due to all the molecules, which depends on the number and distribution of molecules around the chosen one molecule. It not only depends on the number of molecules, it also depends on the distance between them, as molecular forces depend on the distance sometimes. But the average potential energy of all the potential of all the molecules is the same, because if we take this molecule, let's take -1, this molecule also, it's also surrounded by approximately same number of molecules, so the potential energy will be approximately same. Even this molecule, or even this molecule, if we take, it's also surrounded by molecules, it will be same. The only change will come at the surface where it's not same or close to the surface. This attraction results in negative potential energy for the molecule, which depends on the number and distribution of molecules around the chosen molecule, but the average potential energy of all the molecules is the same. And this is also supported by the fact that to take a collection of such molecules and disperse them far away from each other in order to evaporate or vaporize, the heat of evaporation required is quite large. For water, it is order of 40 kg per mole. What they are saying is average potential energy of the molecules is same, and we can understand or support this by, if we take a collection of molecules, like if we take liquid and disperse them far away from each other in order to vaporize, the heat evaporation required is quite large. For water, it is around 40 kilojoule per mole. Not quite understand it, but molecules inside the liquid, there is bulk molecule. A molecule deep inside the liquid is surrounded on all sides by other molecules. All the attractive intermolecular forces balance out, equal pulls in every direction. This molecule has a negative potential energy, that is the bound state. To take that molecule out of that state, we need to provide that amount of potential energy, that negative amount of potential energy, that much work done we should do on that molecule. And its value is the same for all molecules inside. To pull out all molecules to infinity, turn liquid into vapor, we need to supply a lot of energy, that is heat of evaporation. Molecule near the surface, a molecule at the surface has neighbors only on one side, below and sideways, but not above. Since above is air, so it is less strongly bounded than a bulk modulus. Its potential energy is less negative, closer to zero that than that of a bulk modulus. Roughly, its energy is higher by about half of the heat of evaporation per molecule. Conclusion: molecules on the surface have higher energy compared to bulk modulus. That's why even with less energy, they can evaporate easily. Why surface tension arises? Since surface molecules have higher energy, liquid doesn't like to keep too many molecules at the surface. Since surface molecules have higher energy, because the liquid likes to be in a less energy state, which leads to stability, it doesn't like to keep too many molecules at the surface. And to minimize the number of molecules at the surface, the liquid tends to reduce its surface area. That's why drops of liquids are spherical, smallest surface area for a given volume. If you increase the surface area, like stretching a soap film, you need to supply energy to bring more molecules to the surface. What is the surface? Liquids are made up of moving molecules. There is no perfectly sharp boundary. The density of molecules gradually drops from liquid value. Drops from liquid tends to go to minimum energy to minimize the number of high energy molecules. The liquid tries to keep 1 minute. Okay, where was I? Yeah. Molecules at the surface are at higher energy state because they are not fully surrounded by other molecules. Nature always tends to go to minimum energy to minimize the number of high energy molecules. The liquid tries to keep as few molecules at the surface as possible. It can be done by reducing the surface area. If you try to stretch a liquid surface by blowing soap bubbles or pulling apart a film, you must supply extra energy to create more surface molecules. Okay, to increase the surface, basically, because the normally the liquid tends to keep a minimum surface area, it always is in a minimum surface area state for a liquid for a certain configuration. According to the external environment, it will be in the most minimum energy state possible and have the minimum surface possible. Because of that, if we want to increase the surface area more, we need to supply extra energy. Supply extra energy to create more surface molecule. This property of a liquid to contract its surface area due to molecular forces is called a surface tension. What is a surface? At first, it feels like liquid has a sharp boundary with air. Actually, liquids are made up of molecules in constant motion. Near the boundary, say at height z equals 0, just inside the liquid, the density is almost full liquid density. Just outside in the air, the density is nearly 0. But this doesn't change suddenly. Instead, okay, basically, what they are saying is first thing is about this part about potential energy, that one, and this one, which is because molecules are easier to evaporate. Okay, that one is okay. And this one, they're saying what is a surface. Surface is actually, if this is a liquid, there is no sharp boundary like this. We're saying this as the surface and this is air. No, that is not the case. As liquid molecules are constantly moving apart, there will be molecules flying around here as well. And as we go increase height, the molecules will be reducing till a certain height h is reached, where the molecules will be almost zero. And this whole layer where there is molecules in the air, water molecules in the air, all this layer is called as the surface. Let's read it again. A liquid stays together because of attraction of between molecules. Consider a molecule inside a liquid. The intermolecular distances are such that it is attracted to all surrounding molecules. This attraction results in a negative potential energy for the molecule, which depends on number and distribution of molecules around the chosen molecule, but the average potential energy of all the molecules is the same. This is supported by the fact that to take a collection of such molecules and disperse them far away from each other in order to evaporate or vaporize, the heat evaporation required is quite large. For water, it is about 40 kilojoule per mole. If we consider a molecule near the surface surrounded by liquid molecules, there is some negative potential energy due to this, but obviously it is less than a molecule in bulk that is fully inside. Approximately, it is half of the surface molecule. Thus, molecules on a liquid surface have some extra energy in comparison to molecules in the interior. A liquid thus tends to have least surface area, which external conditions permit. Increasing surface area requires energy. Most surface phenomena can be understood in terms of this fact. Increasing surface area needs energy. What is the energy required for having a molecule at the surface? As mentioned above, roughly it is half the energy required to remove it entirely from the liquid, because inside it is -1 delta U and outside it is at the surface it is minus 0.5. Completely outside, infinitely far away, it is 0. So to take it away from surface or take it from inside to surface, we need 0.5 joules of energy in our example case. Since a liquid consists of molecules about, as mentioned above, roughly for what is the energy required for having a molecule at the surface, it is roughly half the energy required to remove it entirely from the liquid. What is surface? Since a liquid consists of molecules moving about, there cannot be a perfectly sharp boundary line. The density of the liquid molecules drops rapidly around z equals 0 as we move above the liquid surface in distance of the order of a few molecular sizes. Okay, then let's go to the next topic, that is about surface energy and surface tension. It's a subtopic, as we have discussed that an extra energy is associated with surfaces of liquids. The creation of more surface, spreading of surface, keeping other things like volume fixed requires additional energy. To appreciate this, consider a horizontal liquid film ending in bar free to slide over parallel guides. Stretching a film in equilibrium, the film stretched an extra distance. Basically, there is a water. Here, we apply something like a cover slip and spread it. And during this spreading, we experience some force, even if it's a frictionless surface. That force is due to the energy required to take water molecules to the surface. Suppose that we move the bar by a small distance d as shown. Since the area of the surface increases, the system now has more energy. This means that some work has to be done against the internal force. Let this internal force be F. The work done by the applied force is F dot D, FD. From the conservation of energy, this is stored as additional energy in the film. If the surface energy of the film is S per unit area, the extra energy is 2dl, that is area, to extra, basically a rectangle which we added, 2 times of dl, where d is a small distance we moved. Area of triangle formula, rectangle formula, film has two sides and the liquid in between, so there is two surfaces, and the extra energy which is equals to 2dl, which is equals to f dot d. If the surface energy of the film is S per unit area, the extra area is 2dl, area times surface per unit area, energy per surface per unit area, which is equals to force times distance. So surface energy, which is equals to F times F by 2L. The quantity S is the magnitude of surface tension. It is equal to the surface energy per unit area of the liquid interface. It is also equal to the force per unit length exerted by the fluid on the movable bar. So far we have talked about surface of one liquid. More generally, we need to consider fluid surface and contact with our liquids. Or before going to that, let's derive this ourselves. Let's take, this is a surface or something like that. This is a water film. This length is L, and this is initially. Now we spread it. Now we spread it like this by applying a force. This way, and small distance d. This is the area, or we don't need that area right now. Now let's take S, energy, surface energy, surface energy per unit area, work done, which is equals to F dot D. Now surface energy per unit area times the distance we moved, that is L times D area. The area we increased is L times D. So L times D times 2, that is rectangle area, 2 times dl, which is equals to work done, F dot d, d cancel, S to L is equals to F, and S will is equals to F by 2L. This is the magnitude of surface tension. This is the derivation. Now let's come back here. The quantity S is the magnitude of surface tension is equal to surface energy per unit area of liquid interface and is also equal to force per unit length exerted by the fluid on the movable bar. So far we have talked about the surface of one liquid. More generally, we need to consider fluid surface in contact with other fluids or solid. The surface energy is in that case depends on materials on both sides of surface. For example, if molecules of material attract each other, surface energy is reduced, which is while if they repel each other, surface energy is increased. Thus, more appropriately, the surface energy is the energy of the interaction between two materials and depends on both of them. Basically, if we take liquid, this is liquid or fluid. Now let's take it as liquid itself. Liquid, and now there is a surface here, and it is attracting the water molecules due to molecular forces attracting. Then for the molecules to come up, there will be more attraction. Because of that, the surface energy will be reduced. Because there is a one more force pulling them up, the surface energy will be reduced. We can, because there is also already a pulling force, the energy required to increase the surface will reduce then. But what if this is what liquid. Now if there is a surface which is repelling the water molecules, then there is one more force pulling them to downward, putting them downward. Because of that, the energy to increase the surface, that is pull more molecules toward the surface, is increased because we need to do work done on the molecules against the repelling force, to take them to the surface. Okay, that is that. Now let's come back. We make the following observation from above. Surface tension is force per unit length or surface energy per unit area acting in the plane of the interface between the plane of the liquid and any other substance. It also is the extra energy the molecules at the interface have as compared to molecules in the interior. It is the extra energy that molecules at the interface have, that surface have, compared to molecules in the interior. It is a force per unit length, surface energy per unit area, acting in the plane of interface between the plane of liquid and any other substance. At any point of the interface besides the boundary, we can draw a line and imagine equal and opposite surface tension force S per unit length of the line acting perpendicular to the line in the plane of the interface. At any point on the interface besides the boundary, we can draw a line and imagine equal and opposite forces, surface tension forces per unit length of line acting perpendicular to the line in the plane of the interface. The line is in equilibrium. To be more specific, imagine a line of atoms or molecules at the surface. Atoms to the left pull the line towards them, those to the right pull it towards them. This line of atoms is in equilibrium under tension. If the line really marks the end of the interface, as in figure 10.16, and B, there is only the force S per unit length acting inwards. If we think of liquid surface as a stretched sheet, molecules at the surface are being pulled sideways by their neighbors. These pulls act along a plane of the surface. This creates a situation similar to stretched elastic string or rubber sheet, always under tension. Now imagine line drawn on the surface. Pick any arbitrary line, say a straight line on the surface, not touching the boundary. Molecules on the left side of the line pull the molecules on the line leftward, molecules on the right pull it rightward. The two sides of pull are equal and opposite, so the line remains in equilibrium. Mathematically, these pulls correspond to a force of surface tension S per unit length acting along the plane in the plane of the surface. At the edge boundary of the surface, if the line you draw ends at boundary of the liquid, say edge of a soap film or meniscus, the molecules are missing on one side. In that case, there is no balancing pull from missing side, so the line experiences a single inward force of surface tension as per unit length. This is why surface tension forces act inward along the boundary, trying to shrink the surface. In simple analogy, inside the interface, balance tug of war, forces cancel out, but tension exists. At boundary, no pulling on the outside, unbalanced inward pull, surface contracts. Okay, then this table gives the surface tension of various liquids. The value of surface tension depends on temperature. Like viscosity, the surface tension of liquid usually falls with temperature because higher the temperature, higher the energy of the fluid, then lower the surface tension because the surface molecules would have mostly evaporated, will have higher energy, and because of that the attraction forces between them will reduce, and surface tension, the pulling tug of war, will also reduce. Surface tension of some liquids has the temperature indicated with the heats of the vaporization. Temperature: helium at temperature minus 270 centigrade, the surface tension is very less. Heat of vaporization, which is 0.115. Oxygen 183, it is 0.0132. Heat of vaporization is 7.1 kilojoule per mole. Ethanol with at 20 degrees, mercury having the highest surface tension. A fluid will stick to a solid surface if the surface energy between the fluid and the solid is smaller than the surface energies of Okay, then let's continue. Surface tension of some liquids at temperature. Okay, a fluid will stick to a solid surface. The surface energy between the fluid and the solid is smaller than the sum of the surface energies between solid and air, fluid and air. Now there is attraction between solid and air, fluid and air. Now there is attraction between the now there is attraction between the solid surface and the liquid. It can be directly measured experimentally as schematically shown in figure 10.18, measuring surface tension. A flat vertical glass below which is a vessel of some liquid is kept forms one arm of the balance. The plate is balanced by weights on the other side with its horizontal edge just over water. The vessel is raised slightly till the liquid just touches the glass plate and pulls it down a little because of the surface tension. Weights are added till the plate just clears the water. Suppose the additional weight required is W. Then from equation 10.22 and the discussion given there, the surface tension of the liquid interface, which is equals to force by 2L, which is equals to W by 2L, where M is the extra mass and L is the length of the plate edge. The subscript LA emphasizes the fact that liquid air interface tension is involved. Okay, what they are saying is a fluid will stick to a solid surface if the surface between the fluid and the surface energy between the fluid and the solid is smaller than the sum of surface energies between solid air and fluid air. Meaning surface energy, meaning like if there is less surface energy, then this can be measured experimentally as schematically shown. We take a flat vertical glass below which, let's understand it more. Condition for sticking condition for sticking a fluid to a solid. Whether a fluid wet sticks to a solid depends on relative surface energy. If the liquid solid surface energy is smaller than if the liquid solid surface energy is smaller than sum of solid air and liquid air. How to measure surface tension? Force method. Take a flat glass plate as one of the arms of balance. On the other side, it weighs, balance it with weights so it floats just above the water. Now raise the vessel of liquid until it touches the glass plate. Because of surface tension, the liquid tries to cling the glass plate and pulls it downward. This makes the balance tilt. Balancing the pull to bring back, you add small weights of other arm. Suppose the extra weight needed W equals mg. The added weight is exactly equal to pull of surface tension on the glass. Y factor of 2L, the liquid pulls along the contact line between liquid and solid. For a flat plate of width L, there are two edges in contact with the liquid, front and back of the plate. So total length of contact is 2L. The force due to surface tension is force, which is equal to surface tension into length of contact line, F, which is equal to S into 2L. Work done, which is again equal to okay, then let's go back. The new subtopic, that is angle of contact. Right. The surface of liquid near the plane of contact with another medium is in general curved. The surface of liquid near the plane of contact with another medium is generally curved due to the surface energy. It is going inside, so it will curve. The angle between tangent of the liquid surface at the point of contact and solid surface, the liquid, is termed as the angle of contact. It is denoted by theta. It is different at interfaces of different pairs of liquid and solids. The value of theta determines whether a liquid will spread on the surface of a solid or it will form droplets on it. For example, water forms droplets on lotus leaves as shown in figure 10.19a while spreads over a clean plastic plate. This is a lotus surface. It's forming angle theta here, that is angle of contact. Now it sticks in case of plastic, which is below 90 degrees, and it is theta. Different shapes of water drops with interfacial tensions A and A on a lotus leaf, P on a clean plastic plate. We consider the three interfacial tensions at all three interfaces: liquid air, and solid liquid, denoted by SLA, SSA, and SSL respectively, as given in figure 10.19a and b. Due to surface, due to a tension between a surface and air, which is in this direction, surface and liquid, which is in this direction, and surface liquid and air, which is in this direction. At the line of contact, the surface forces between the three media must be in equilibrium. Following the relation easily derived is SLA cos theta plus SSL, which is equals to SSA. The angle of contact is an obtuse angle if SSL is greater than SLA, as in the case of water leaf interface, or it's an acute angle if SSL is smaller than SLA, as in the case of water plastic interface. When theta is an obtuse angle, then the molecules of water are strongly attracted to themselves and weakly to those of solid. It costs a lot of energy to create liquid solid attract surface, and liquid then does not wet the solid. This is what happens with water on a waxy or oily surface and with mercury on any surface. On the other hand, if these molecules basically what it means when a liquid is in a spherical shape and what it means when it is sticking to the surface is, if the attraction between surface and the liquid is strong, then this kind of thing is formed, whereas liquid or a liquid will stick to the surface when attraction between the liquid and the surface is very strong. But if the attraction between the water molecules is greater than the attraction of surface, then the water will not stick to the surface. This will not happen when water molecules have stronger attraction than the surface, like in lotus leaf case, where it does not stick to the water because there is a cuticle which is there on leaves, which is a waxy layer which will prevent the water from sticking. It does not attract the water molecules. If the molecules of liquid are strongly attracted to those of the solid, this will reduce SSL, and therefore cos theta may increase or decrease. In this case, theta is an acute angle. This is what happens for glass on water slide, water on glass or on plastic, and for kerosene oil on virtually anything. It just spreads. Kerosene doesn't have any kind of attraction forces in itself, so because of that it just spreads on virtually anything. Soaps, detergents and dyeing substances are wetting agents. When they are added, the angle of contact becomes small so that these penetrate well and become effective. Waterproofing agents, on the other hand, are added to create a large angle of contact between the water and the fibers. Basically, when detergents or any kind of wetting agents are added, then they will basically make the drop like this so that they can penetrate into the fibers of a cloth to clean it well or other kind of uses. If it is waterproofing is done, waterproofing agents do increase the angle theta, that is angle of contact, so that the water does not wet the substance. Next subtopics, drops and bubble. One consequence of surface tension is that free liquid drops and bubbles are spherical if effects of gravity can be neglected. You must have seen this especially clearly in small drops just formed in high speed spray or jet and in soap bubbles blown by most of us in childhood. Why are drops and bubbles spherical? What keeps soap bubbles stable? As we have been saying repeatedly, a liquid air interface has energy. So, for a given volume, the surface with minimum energy is one with the least area. The sphere has this property. Though it is out of scope of this book, but you can check that a sphere is better than at least a cube in this respect. So, if gravity and other forces, air resistance were ineffective, Liquid drops would be spherical. That's why when air jet or any kind of spray like here they mentioned here liquid drops are spherical. Okay, small drops formed in high speed spray or jet. In this case, air resist because of the small size of the droplets. Air resistant doesn't work. Gravity for such minute mass is very negligible, etc. Because of their minute mass, it is possible they ignore all kind of effects, and water will have its least or most stable state with least energy. Another interesting consequence of surface tension is that pressure inside a spherical drop is more than the pressure outside. Suppose a spherical drop of radius r is in equilibrium. If its radius increased by delta r, the extra surface energy is this equation 8 pi r delta r SLA. If we assume that a spherical drop of radius r, it is in equilibrium, but if its radius increases by delta r, the extra surface energy is 8 pi r delta r SLA. If the drop is in equilibrium, this energy cost is balanced by the energy gain due to expansion under pressure difference. The energy cost, if there is a pressure difference and the pressure inside is more than the pressure outside, then the bubble can or the water drop can expand due to by balancing out the pressure, like how the water streamlines which became faster due to decrease in pressure. Same way the surface energy can be accommodated by compensating with the pressure difference between the inside of the bubble and the outside. The work done which is equals to pi minus p naught 4 pi r square delta r. 4 pi r square is the area change in pressure, p times a which is equals to force times delta r or force times displacement, which is equals to work done. So that p minus p naught which is equals to change in pressure, which is equals to 2SLA by r. In general, for a liquid-gas interface, the convex side has a higher pressure than the concave side. For example, an air bubble in a liquid would have higher pressure inside it. Air bubble in liquid would have higher pressure inside it. Drop cavity and bubble of radius r. A bubble figure 10.20 differs from a drop and a cavity. This is a drop, there is no cavity here. There is a cavity here, and this is a bubble. It's completely a bubble. In this, it has a bubble and a cavity have two interfaces. Applying the above argument, we have for a bubble pressure difference which is equals to 4SLA by R. This is probably why you have to blow hard but not too hard. Because the pressure inside is more, you need to blow in more air to form a soap bubble. A little extra air pressure is needed inside. Capillary rise. One consequence of the pressure difference across a curved liquid-air interface is well-known effect that water rises up in a narrow tube in spite of gravity. The word capilla means hair in Latin. If the tube were hair thin, the rise would be very large. To see this, consider a vertical capillary tube of circular cross-section radius A. Insert inserted into an open vessel of water. The contact area between water and the glass is acute. Okay. What is the consequence between pressure difference is that one consequence of pressure difference across a curved liquid air interface is a well-known effect as the water rises up in a narrow tube in spite of gravity. The rise would be very large to see. Consider if vertical capillary tube of circular cross section, radius inserted into one open vessel of water. The contact angle between water and glass is acute, thus the surface of water in the capillary is concave. This means that there is a pressure difference between the two sides of the top surface. This is given by this equation here. Thus, the pressure of the water inside the tube just at the meniscus air-water interface is less than the atmospheric pressure. Consider the 2 points A and B in figure 10.21a. They must be at the same pressure, namely P naught plus H rho G, which is equals to P1, which is equals to Pa, where rho is the density of water and H is called the capillary rise. Using equation 10.2 and 10.30, we have H rho G, which is equals to P1 minus P naught, which is equals to 2S cos theta by A. The discussion in here and the equations make it clear that the capillary rise is due to surface tension. It is larger or smaller. A, typically it is of the order of few centimeter, or for fine capillaries, for example, if A equals 0.05 centimeter, using the value of surface tension for water, we find that H, which is equals to this much value, and approximately it will be 2.98 centimeter. Notice that if the liquid meniscus is convex, as for mercury, that is if cos theta is negative, then from equation 10.30, for example, it is clear that liquid will be lower in the capillary. Detergents and surface tension. We clean dirty clothes containing grease and oil, stains sticking to cotton or other fabrics by adding detergents or soap to water, soaking clothes in it, and shaking. Let us understand this process better. We saw that soap was acting as a wetting agent where it will let the water soak into the fibers and clean it neatly. Washing with water does not remove grease stains. This is because water does not wet greasy dirt. That is, there is very little area of contact between them. If water could wet grease, the flow of water could carry some grease away. Something of this sort is achieved through detergents. The molecules of detergents are hairpin shaped with one end attached to water and the other to the molecules of grease, oil, or wax, thus tending to form water-oil interfaces. The result is shown in figure 10.22 as sequence of figures. In our language, we would say that addition of detergent whose molecules attract one end and say oil and the other end reduces drastically the surface tension of water oil. It may even become energetically favorable to form such interfaces, that is globs of dirt surrounded by detergents and then by water. This kind of process using surface active detergents or surfactants is important not only for cleaning but also in recovering oil, mineral ores, etc. Water, we add soap molecules will attracted to water, platter with particles of greasy dirt. Water is added, dirt is not dissolved. Detergent is added, the inert waxy ends of its molecules are attracted to the boundary where water meets dirt. Inert ends around the dirt, and flatter dirt can now be dissolved by moving water. Dirt is held suspended, surrounded by soap molecules. Detergent action in terms of what detergents molecules can do. Let's see, lower end of a capillary tube of diameter 2 millimeter is dipped 8 centimeter below the surface of water in a beaker. What is the pressure required in the tube in order to blow a hemispherical bubble at its end in water? The surface tension of water at temperature of the experiments is 7.3 into 10 power minus 2 Newton per meter, 1 atmospheric pressure, which is equals to 1 atm, density of water, which is equals to 1000 kg per meter cube, G, which is equals to 10 we can take, but they give 9.80. Also calculate the excess pressure. The excess pressure in a bubble of gas in a liquid is given by 2s by r, where s is the surface tension of liquid gas interface. We should note that there is only one liquid surface. In this case, for bubble of liquid in gas, there are two liquid surfaces. So the formula for excess pressure in the case is 4s by r. The radius of the bubble is r. Now the pressure outside the bubble is P atmosphere equals atmospheric pressure plus the pressure due to 8 centimeter of water column. That will be 1.01784, which is similar to atmospheric pressure. Therefore, the pressure inside the bubble is Pi, which is equals to P naught plus 2S by R, which will get us 1.02 into 10 power 5 Pascal, where radius of the bubble is taken to be equal to the radius of the capillary tube, since the bubble is hemispherical. The answer has been rounded off to 3 significant figures. The excess pressure in the bubble is 146 Pascal. Okay, with that, the chapter concepts are done. Let's see a summary. The basic property of fluid is that it can flow. The fluid does not have any resistance to change of its shape. Thus, the shape of fluid is governed by the shape of its container. A liquid is incompressible and has a free surface of its own. A gas is compressible and it expands to occupy all the space available to it. If F is a normal force exerted by fluid on an area A, the average pressure PAV, which is defined as ratio of force to area. The unit pressure is Pascal. It is same as Newton per meter square. Other common units are important to remember. 1 atm, which is equals to 1.01 into 10 power 5. 1 bar, which is equals to 10 power 5 Pascal, similar to 1 atm. 1 torr, which is equals to 133 Pascal or 0.133 kilopascal. 1 mm of Hg, which is equals to 1 torr, which is equals to 133 Pascal. Pascal's law states that pressure in a fluid at rest is same at all points which are at the same height. A change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and the walls of the containing vessel. The pressure in a fluid varies with depth h according to the expression P, which is equals to Pa plus rho gh. The rho is the density of the fluid, the assumed uniform. The volume of the incompressible fluid passing any point every second in a pipe of non-uniform cross-section is the same in the steady flow. Va, which is equals to constant, where V is the velocity and A is the area. The equation is due to mass conservation in incompressible fluid flow. Bernoulli's principle states that we move along a streamline, the sum of the pressure, the kinetic energy per unit volume, and the potential energy per unit volume remains constant. The equation is basically the conservation of energy applied to non-viscous fluid motion in steady state. There is no fluid which has zero viscosity, so the above statement is true only approximately. This viscosity is like friction and converts kinetic energy to heat energy. Though shear strain in fluid does not require shear stress, when a shear stress is applied to fluid, the motion is generated which causes a shear strain growing with time. The ratio of the shear stress to the time rate of shearing strain is known as the coefficient of viscosity, where symbols have their usual meaning and are defined by the text. Stokes' law states that viscous drag force F on a sphere of radius A moving with a velocity V through a fluid of viscosity is F, which is equal to 6 pi eta AV. Surface tension is a force per unit length acting to the plane of interface between the liquid and the bounding surface. It is the extra energy that molecules at interface have compared to the interior. That's the summary points to ponder. Pressure is a scalar quantity. The definition of pressure as force per unit area may give one false impression that pressure is a vector. The force in numerator of the definition is component of the force normal to the area which it is impressed. While describing fluids as a concept, shift from particle and rigid body mechanics is required. We are concerned with properties that vary from point to point in a fluid. One should not think of pressure of a fluid as being exerted on a solid like that walls of a container or a piece of solid matter immersed in fluid. Pressure exists at all points in a fluid. An element of a fluid such as the one shown in figure 10.2, like taking a cylinder element in equilibrium because the pressure exerted on the various places are equal. The expression for pressure, which is equals to P, which is equals to Pa plus rho gh, holds true if fluid is incompressible. Practically speaking, it holds for liquids which are largely incompressible and hence is a constant with height. The gauge pressure is the difference of the actual pressure and the atmospheric pressure, P minus Pa, which is equals to Pg. Many pressure measuring devices measure the gauge pressure. These include the tire pressure. What is gauge pressure? Gauge pressure is the difference of the actual pressure and the atmospheric pressure. Many pressure measuring devices use the gauge pressure. They include tire pressure gauge, blood pressure gauge, sphygmomanometer. A streamline is a map of fluid flow in steady flow. To streamlines do not intersect, as it means the fluid particle will have two possible velocities at the point. Bernoulli's principle does not hold in presence of viscous drag on the fluid. The work done by dissipative viscous force must be taken into account in this case, and P2 will be lower than the value given by equation 10.12. As the temperature rises, the liquid becomes more mobile and the coefficient of viscosity falls. In a gas, the temperature rises, increasing the random motion of atoms and increases eta, coefficient of viscosity. Surface tension arises due to excess potential energy of the molecules of the surface in comparison to their potential energy in the interior. Such a surface energy is present at the interface separating the two substances, at least one of which is a fluid. It is not the property of a single fluid alone. Surface energy is present at the interface separating the two substances, at least one of which is a fluid. With that, we have completed first revision of this chapter via NCERT.